Uh, if you recall what we have discussed so far, we had looked at the different ways of realizing a given function in the form of an expression, sum of products, product of sums, and we talked about several methods using which you can minimize the size of the expression, so that the resulting gate level realization becomes cheaper in some respect. Number of gates can be smaller, the size of gates can also be smaller. Now, let us look at some real circuits and how we can design those circuits and apply them in various applications. So, we shall be looking at the design of such basic building blocks which can be used to build larger systems. To start with, we will look at the most fundamental thing that we need in many applications. Think of an adder. We need to add numbers in almost any applications you can think of. So, we shall be starting by talking about the design of adders, and after that we shall be looking into some other very commonly used functional blocks. Okay. So, the title of this lecture is Design of Adders. So, before we move into the design of adders, so as I said, we shall be discussing over the next few lectures the design of various commonly used so called combinational circuit modules. So, let us first try to understand what is a combinational circuit. See, the definition of a combinational circuit is like this. Suppose I have a circuit where there are some inputs, there are some outputs. Now, if the circuit is such that the outputs will depend only on the inputs that I have applied at that point in time, and they have no bearing on the past history of the inputs. Past history, what happened earlier, what inputs were applied earlier, that will not have any bearing on what the output is coming. So, such a circuit is called a combinational circuit, where the output will depend only on what inputs we are applying at this particular point in time. So, you think of an adder, an addition. I apply two inputs to be added, I get the sum as the output. This is an example of a combinational circuit. Okay, we talked about a multiplexer. We have the inputs, we have the select lines, we select one of the inputs and that go to the output. That is also a combination circuit. But you think of an application like this, well, you have all seen the traffic light controller in the intersection of the roads. See, the sequence in which the lights glow, that is not arbitrary. Red, orange, green, then again orange, then red, again orange, then green. There is a particular sequence. So, when the lamp is orange, so what will be the next state, what will be the next lamp that will be glowing? That will depend on the past history. If previously red was glowing, then the next will be green, and if previously green was glowing, then the next will be red. This is an example of a so called sequential circuit, which we shall be discussing later, where the output that we get depends not only on what we have now, but also some previous history of the system. Okay. So far here we are talking only about combinational circuits. Okay. Some of the very common examples of combinational circuits that we shall be discussing are, okay, first we shall be talking about adders and subtractors. Multiplexers we already have talked about earlier, we shall be looking into it again, decoders and demultiplexers and encoders. These are the some of the functional blocks that we shall be going into some detail. So, we start with addition. Okay. We already talked about the problem of adding binary numbers. We talked about the binary number system. We talked about how you can add two binary numbers. We start from there. From there you will get some idea that how we can design a circuit that can actually carry out addition. Okay? Let us see. First we take a very simple sub problem, addition of two binary digits or bits. This is the truth table. So, I have two input bits A and B. So, I am adding them, I get a sum, I get a carry. S is the sum and C is the carry. What are the rules for addition? You already know this. If we add 0 and 0, the sum is 0, which in binary you can write 0 0. If we add 0 and 1, sum is 1 0 1. If we add 1 and 0, again sum is 1 0 1. If we add 1 and 1, sum is 2. So, in binary it is 1 0, that is why I have used 2 bits, because in 1 bit you cannot represent the sum, 1 plus 1 is 2 1 0. You see this truth table actually shows this. The last bit is the sum 0 1 1 0, you see 0 1 1 and 0, and this is the carry 0 0 0 1, right. Okay. So, we want to design such a circuit, and a circuit which does this is called a half adder. So, the definition of a half adder is that half adder takes two binary digits or bits as input A and B, it produces a sum, it produces a carry, and this is the truth table of a half adder. Now, directly from truth table, if you write down the expression that what is the switching function that is realized by the sum and the carry, you first look at the sum. Sum has a true minterm here, it has a true minterm here. You see inputs are 0 1 and 1 0. 0 1 means A bar B, 1 0 means A B bar. You see here we have written exactly that, A bar B or A B bar, which is nothing but the exclusive OR function. So, sum is nothing but the exclusive OR of A and B. Okay. If you look at the carry, carry has a single true minterm corresponds to 1 1, which is A B. So, carry is nothing but A B. So, if you implement such a half adder using gates, the sum you can implement by a single exclusive OR gate, the carry you can implement using a single AND gate, right. Now, one thing to note is that exclusive OR is sometimes not regarded as a basic gate. So, if you want to implement an XOR gate, maybe you will be using a function like this, like you will be using two AND gates like this, then there will be an OR gate, output of the AND will go to the input of the OR. First one will get A bar B. So, the input A is there. So, there will be a NOT A bar and B will be fed to the second input. Second one will A B bar. So, this A will be fed here and B will be fed with a NOT to here. This is the implementation of a exclusive OR function A XOR B. Now, let us see, if we say that delta is the delay of a basic gate, we shall also talk about this later. Basic gate means AND, OR and NOT. These are regarded as the basic gates. Then for generating carry, the delay is only delta, there is a single AND gate. But for sum, if I realize using this, you see firstly there is a NOT, then there is AND, then there is OR. There are 3 levels. So, the delay will be thrice delta. So, you should remember this, if delta is the delay of a basic gate, then for a half adder sum will require 3 delta and carry will require only delta to generate. Okay. Fine. Now, from here let us talk about how you can add multiple bits, multi-bit numbers. This we have already discussed earlier, let us look at it once more. Suppose I have a number A, I have a number B, these are the example I have taken, these are 7-bit numbers. So, I am adding 1 and 1, sum is 0 with a carry of 1. Then I am adding all these numbers with carry 1, 1 and 0, sum is 0 again with a carry of 1. 1, 0, 0, sum is 1, but no carry. 0, 1, 1 is 0 with a carry. 1, 0, 0 is 1 with no carry. 0, 1, 0 is 1 with no carry. 0, 0, 0 is 0. Okay. So, you see when you are actually adding two numbers, multi-bit numbers, we also need to take care of the carry. We need to check the carry from one stage to the next. These are called the stages. For a 7-bit number, I say that these are 7 stages of addition. The first stage of addition generates a carry which is used in the second stage. Second stage of addition generates a carry which is used in the third stage, okay, like this. Let us take another example. So, where the numbers are like this 0 followed by all ones and the second number is just 1. This is an example where you see that the carry will be propagating up to the last position. You see 0, so initially there is no carry, initially carry is 0. So, 0 1 1 will generate sum of 0, carry of 1, 1 1 0 sum 0, again carry of 1, same thing sum 0, carry 1, sum 0, carry 1, this will continue, right. So, you see there is a carry propagation from the last stage to the most significant stage. So, the reason I have taken this example is that later on you will see when we calculate the delay of such a adder, we will have to take care of this carry propagation time. If it is an 8-bit adder, it must propagate from stage 0 up to stage 7. We will have to take care of this entire carry propagation time. Okay. So, one observation from here is that you see in every stage that we have shown in this example, we are requiring to add 3 bits. 2 bits are the bits of the number and the third bit is the carry which is coming from the previous stage. So, 1 bit of number A, 1 bit of number B and a carry bit coming from the previous stage. So, earlier we talked about a half adder which can add only 2 bits, right. Inputs were A and B, output were sum and carry. But here we need another kind of a adder which can add 3 bits, not only A, B, but also there will be a carry input, 3 inputs. Okay. So, we need another kind of an adding block which is called a full adder. Full adder basically can add 3 bits. Let us look at full adder, what a full adder is. Full adder, as I said, we will have 3 inputs. The 3 inputs are the 2 input bits A and B and the carry input, let us say C in, carry in. And again there will be 2 outputs, one is the sum, other is the carry output, let us call it C out. Now, we shall see later that when you have multi-bit numbers, we can use a cascade of full adders, because you see exactly the way we did the addition by hand. We add 3 bits, carry was generated, again we added 3 bits, carry was generated, again we added 3 bits. So, if you have several full adders connected one after the other, the same thing can be implemented. The idea is like this. Okay. So, a full adder schematically can be shown like this, where A, B and C in are the inputs and S and C out are the outputs. The truth table for the full adder will look like this. This was also seen earlier. So, A, B, C are the 3 inputs. If you add them, 0 0 0 is 0, that means 0 0. Okay, C out will be, So, when you consider the value of the number, you consider it as C out as the most significant, then S in that order. 001 is 1, 01, 010 sum is also 1, 01, 011 is 2, 10, 10 is 2, right, 100 is 1, 01, 101 is 2, 10, 110 is also 2, 10, 111 is 3, 11, right. This is the truth table of the full adder. Now, again from this truth table you can write down the expression for the sum and the carry. For the sum, you see there are 4 true minterms. If we just write them down, 001, which is A bar, B bar, C in, 010, A bar, B, C in bar, 100, A, B bar, C in bar, and 111. So, this again is nothing but the exclusive OR of the 3 numbers A, B and C in. Similarly, when you look at the carry out, here again there are 4 true minterms corresponding to 011, which is A bar, B, C in, 101, 110 and lastly 111. So, if you minimize this using Carnot map or any other method, you will see that the minimum form is A B plus B C in plus A C in. So, when you implement a full adder like this using this expression, what you need is that for the first case for sum, you need either a big XOR gate with 3 inputs, and for carry you will be needing 3 AND gates A B, B C, C A and an OR gate. So, each of these AND gates will be having 2 inputs each. First one will be fed with A and B, next one with B and C in, B and C in, and last one with A and C in, A and C in, like this, and output will be C out. And here the inputs will be A, B and C in, and the output will be S. Now, again because this XOR gate is not a basic gate, if you want to implement them using AND gates, suppose this first expression you look at, then you will be needing 4 bigger AND gates, okay, each with 3 inputs, because there are 3 literals, each with 3 inputs. Then there will be a 4 input OR gate connecting the output of these AND gates, and to generate this A bar, B bar and C bar, there will be some NOT gates also in the input. I am not showing the exact circuit, you can draw this. So, in terms of delay again, here you see this XOR gate again will be having a delay of 3 basic gates. First stage are the NOTs, then the AND, then the OR. But for carry out here again there is a AND and an OR, there is no NOT here, 2. So, if you look at the delay here, for a sum the delay will be 3 delta, where delta is the delay of a basic gate, and for carry out it will be twice delta, delta is the delay of a basic gate, right. Okay. There are other ways of implementing a full adder. So, I am showing a couple of such designs where you can possibly reduce the number of gates a little bit. See, earlier for carry out we had used 3 AND gates and a 3 input OR gate. So, here we are making a shortcut. First thing is that the sum earlier was generated by a 3 input XOR, you recall. Now, a 3 input XOR gate can also be implemented as a cascade of 2 input XORs. If these are A, B and C in, you can have A, B here, you can have C in here, these two are equivalent. So, here we have done the same thing for generating sum, and for generating the carry we are taking the output from this place. Well, do not ask me how we arrived at this. This is more like an art, there is no systematic procedure for this. Somehow someone has come up with this design which requires less number of gates, and this can also generate the same carry out. Let us check. So, what is the value here? It is XOR of A B. Okay. What is XOR of A B? A bar B or A B bar. This is XOR of A and B. In this AND gate, we are ANDing this with C in. Okay. Okay, just for convenience, I am writing only C in for simplicity. And the second gate is just the AND of A B. So, OR A B. This is what I get. Let us see what this expression is. The first one is A bar B C or A B bar C or A B. Now, you recall we have A B bar C and A B. So, what does this mean? A B bar B C plus A B. If you take B common here, it will be A bar C plus A. Now, you recall a rule which you discussed earlier. This A bar C or A is nothing but C or A, which means B C or A B. So, I can write this only B C. So, exactly in the same way, this A B bar C and A B, if you combine, take A common, it will be B or C. So, it will be nothing but A C, and this A B is already there. So, you see you get the same expression for carry out. So, this is a simpler way using one extra gate and also smaller gate here, OR gate is also smaller, 2 input, right. Okay. There is another way to implement a full adder, that is using half adders. So, this I leave this as an exercise for you to verify that whether this C out and S that is being generated is correct or not, because already you know what is a half adder. So, if A B are the inputs, the carry is nothing but A B and sum is nothing but A XOR B. In this half adder, you are again applying the third input with A XOR B. So, sum will be correct, A XOR B XOR C, sum is obviously correct, but you will have to check this A XOR B or A B. This is what is carry out. So, this I leave as an exercise for you to verify whether this is actually equal to A B. This is the carry, right? No, this is not A B actually. No, I have just made a mistake. Let me correct it. So, A B, this sum is A XOR B, carry is A B. In the next half adder, the inputs are A XOR B and C, let us say C. So, the sum will be A XOR B XOR C, and this carry output will be A XOR B and C. This point will be A XOR B, this is one input and the second input. So, the carry out that we generate finally, this will be OR of these two, OR of A B and this. And I leave it as an exercise for you to verify that this is actually equal to A B or B C or A C. Okay. So, if you have half adders as the building blocks, you can also design a full adder using that. Okay. Fine. Now, using the previous method, so this delays already we have talked about earlier. So, here it is mentioned again. This is the original design of the full adder, where this sum was generated by an XOR function and the carry was generated using A B or A C or B C this way. So, if delta as I mentioned is the delay of a basic gate. So, for carry it requires 2 level of gates, first is AND then OR. So, which is 2 delta, and sum XOR I said XOR can be implemented in 3 levels, first NOT, then set of AND gates, finally OR gates, OR gate 3. So, this will be 3 delta. So, delay of a full adder you can calculate like this: carry will be generated after 2 delta, sum will be generated after 3 delta, right. So, now we shall see in our next lecture. So, what are the different ways to design parallel adders using these full adders and maybe half adders also. So, we shall look at several different kinds of adders, ripple carry adder and carry look adder in some detail, and we shall briefly look at 2 other kinds of adders which are a little more complex. These are a little advanced kind of adders, we shall be looking at them. So, this we shall be discussing starting from the next lecture onward. So, we come to the end of the present lecture, where if you recall we talked about the basic building blocks using which we are now ready to design a parallel adder. We looked at the half adder, we looked at the half adder, the next step the full adder. Now, using these full adders and also half adders if you want, you can design a circuit that can add to in general n bit numbers. This is called a parallel adder. This we shall be discussing in our next lecture. Thank you.